Welcome to next lecture, and in today's lecture what I will do is this. I will rather go to motor operations. Generator operation we have seen, is not, that is load characteristics of separately and shunt generator. It must be told that the rating of DC machines, voltage rating particularly, is very much limited because of commutator segment and mica insulations. You cannot have a machine, DC machine, whose rating is 5 kV, 6.6 kV, no, out of question. It may be at best 1 kV or so because of its limitations in the commutator segment and brushes, there will be flashover. Okay. So, DC machines as generator nowadays is almost obsolete. Let us be very clear about this point. If you want to get DC, okay, AC supply is there, convert it with a solid state rectifier. Even you can get variable output DC voltage by using controlled rectifier, silicon controlled rectifier SCRs, or convert it to DC, then use some DC converter. There are so many good options are there. So, nobody really generates DC power in bulk, hundreds of megawatts, and try to transmit it. No, because the voltage is the limitation. You cannot transmit bulk amount of power over a long distance with a little voltage of 1000 volt generated in the terminals, because if it is DC you cannot step it up. In case of synchronous machine also, the voltage generated is of the order of only 11 kV, but you have transformers AC, step it up, then transmit. Okay. Therefore, DC generators are nowadays not used practically. So, but still DC motors are in use, and we will first tell you how to calculate the performance of a DC machine in terms of how to calculate efficiency, how to calculate torque, this, that. And about DC motor, I will tell that there are two kinds. One is shunt motors or separately excited motor. Shunt motor and another interesting motor, that is called series motor. Okay. And we will try to understand each one of them. There are compound motors also. About compound things I will make a general statement at the end, the computations are similar. Okay. There are the compound generators and compound motors also. In case of separately excited motor, what is done is this: the field winding is this one, this is your armature winding, and here the field circuit is given supply from a separate DC source, V field DC source, fixed DC voltage, then you have a field resistance, this is your field coil, and if you switch on supply, there will be some field current IF, and it will produce flux per pole phi. Okay. Now, if you simply energize this machine with field excitation, nothing is going to happen, because there is no prime mover in case of motor, mechanical load may be present. So, you have to apply a voltage, supply voltage, which I will call it armature supply voltage, which is also DC, of course, it is there. Now, if you apply the rated voltage, machine is suppose stationary. If you apply the rated voltage, suppose the machine rated voltage, armature rated voltage is 220 volt. Why this is doing this? Armature voltage is suppose 220 volt DC rated. Field circuit voltage rated will be also 220 volt. Okay. I have just indicated in this VF and VA wave, because I may vary them in future, separately excited. So, maybe I will have some control. So, apply some 220 volt DC. Now, when you switch on this machine without doing anything, etc., at the moment you close these switches, how much will be the current? Because machine was stationary, machine has got some inertia. So, at t equal to 0 plus, immediately after you have closed this circuit, the current drawn from the supply is called the starting current, and the equivalent at starting condition, I am sorry, this armature can be modeled as some armature resistance RA and the supply VA, nothing else. Because machine has not yet started moving, therefore, there is no generated voltage by the machine, which is called back EMF in this case. So, starting current will be pretty large, I starting is equal to VA divided by RA. RA being very small, starting current will be very large. Will be high. Maybe there will be problems in the machine. Now, first of all, just merely saying that armature resistance is small does not make any sense. Is it milliohm? Is it 1 ohm? I mean, high low is a very selective term. I will first tell about that a little bit. We know that in a DC machine, or for that matter any rotating machine, let us assume the machine has been well designed. Okay. Whoever has designed the machine has designed it well. Then the efficiency of a well designed machine, rotating machine, may be 80 or 85% very well designed machine, but certainly not 90% and above like transformer transformer 99%, very good, there is no rotating part. But in case of DC machines or say induction machines, whatever it is, the order of efficiency may be 85%, 80% like that. Okay. So, you just see globally that suppose you have a 10 kilowatt 220 volt DC machine, or I will take for simple calculation 200 volt, so that I can compute easily. Suppose there is a 10 kilowatt or 5 kilowatt, let us take a 5 kilowatt 200 volt DC machine. What does this mean? It means that your rated voltage you can apply to the armature is 200 volt, rated voltage you can apply to the field is 200 volt. And when the machine will be fully loaded, it will give you an output of 5 kilowatt. That is the whole idea. Acha. Now, let us assume to understand how to estimate the value of RA. Suppose we have purchased a machine, this one, it is delivered. Now, I will say that okay, let this I am choosing, I may be wrong a little bit here and there, but as a practicing engineer it is very useful. Suppose let efficiency of the machine is 80%. Then and this is the output power, mind you, whatever will be written on the motor, in case of induction motor also we have seen, this is the net mechanical power output, net mechanical power output. Okay. So, when the machine will be operating at full load condition, the input, total input must be 5000 divided by 0.8, so much watt, is not how much it is? 6.25 kilowatt you are telling, 6.25 kilowatt, that is equal to 6250 watt. It gives you 5 kilowatt, this is the input. Now, where this remaining power goes? Remaining power will be the total losses in the machine. Assuming it is a well designed machine, this thing I assumed, I have not yet tested the machine, I assumed okay, total input will be of this order. So, total loss will be this 6250 minus 5000. How much? 1250 watt. Now, let us have some idea. This is the total loss. Total loss comprises of what? There will be some copper loss, Ia square Ra, because armature has got resistance. There will be some field copper loss, If square Rf. All things considered, efficiency is to be calculated. We will tell you about that in much detail, but as a common user, there will be an armature copper loss here, field copper loss here. And not only that, there will be another called rotational loss. 3 losses take place primarily, that is the armature copper loss, field copper loss. So, this will be equal to armature copper loss plus field copper loss plus rotational loss, frictional and some eddy current loss takes place in the armature. We will come to that. but these three losses are the primary losses. Now, we do not have any idea of how this 1250 will be distributed in these 3 points. Okay, I do not have any data. Let us assume equal weightage, let us give 1/3, 1/3, 1/3. So assume all the losses are equal, and say armature copper loss will be 1/3 of that. How much it is? 417. So much what? Field copper loss also say 417, that is what I have assumed, is not? Acha. Tell me what will be the rated armature current from this data. Input is this much, input power, that minus the field copper loss will be the power coming from the armature, is not? This input power will be so 6250 minus the field copper loss, which 1/3 of this, how much it is? No, that 417, na? 6250 minus 417 divided by 200, 29 ampere, say 30 ampere will be the armature current. Okay. Then I will say that this armature current I A square into R A is equal to 417 watt. So, R A is how much? Point 0.46. Ohm, 0. This is causing problem. See, try to understand what I am doing here. I am telling that a DC machine is given. We say armature resistance is small. It does not make any sense. Small means what? Milliohm, micro ohm or 1 ohm, whatever it is. You can easily see rated current of the machine I have estimated 30 watt. If somebody says this machine is having 2 ohm resistance armature, you calculate what will be the copper loss when rated current will be flowing. It will be very high, efficiency will be very poor. 2 ohm is also small, what is? Similarly, can I estimate what is the value of field resistance? How much? So, this is an important thing I am telling, which will not be discussed in general books. How much field resistance? I am just estimating, okay, a machine is there. How much is the order of armature resistance of this machine? About 0.46 ohm. When you will measure, it will not be 0.46, will be nearby, maybe 0.5 ohm, maybe 0.6 ohm also. I am not sure, I do not care, but I have got some idea of the order of the armature resistance, that is important. How much? Field winding resistance, that is Vf square divided by Rf is equal to 417. So, of the armature field circuit resistance RF will be, I mean field coil resistance, this is RF external mind you, field coil resistance will be 96 ohm, say 100 ohm, maybe 120 ohm. So, what for a well designed DC machine, armature resistance for this DC machine will be of the order of 0.46 ohm or 0.5 ohm or 0.6 ohm, and field circuit resistance will be of the order of hundreds ohm, I mean maybe 120 ohm. These are not at all the measured value at all. Therefore, if I now come to the starting problem of the DC machine whose rating is 5 kilowatt, 200 volt DC motor, somebody writes, say separately excited, it will separately excited machine can be connected as shunt machine like generator, separately excited motor. Estimated values of RA is about 0.5 ohm, that is what we have found out. Field coil resistance, mind you it is no external resistance, field coil resistance is of the order of 100 ohms, like that. That is what we have got. Now, if this machine and its rated current we have already got, IA rated is how much? 30 ampere, approximately 30 ampere. Now, if such a machine, what I am trying to tell, if field is given full voltage, no external resistance 200 volt you give, it develops rated flux, fine, and then you apply full voltage, $200 here, and the order of armature resistance is at starting, there is no back EMF coming in at starting. This is 0.5 ohm. The current drawn will be IA starting will be 400 ohm, 400 ampere, 400 ampere. Rated current is 30. So, many times the rated current will be flowing, 400 divided by 30, if you do about 14 times the rated current will be flowing. This may cause problem, armature may burn, this that, but depends on, because machine will not such a large current will flow, but machine will also start running. The moment it starts running, the equivalent circuit changes 200 volt. It is at the time of closing the switch 400 volts. Then machine starts picking up speed. This voltage appears, which will oppose the supply voltage, and this current will fall. Now, the question is if the inertia of the machine is large, this level of starting current will persist for a longer time. If machine picks up speed very slowly because of high inertia, this level of current will be there for longer time, and then it is really a problem. But if the same machine is having very low inertia, then okay, 400 ampere, but quickly picks up speed. That may not be that alarming. It depends upon so many things. But the point is, we will always try to avoid such a scenario, that give full voltage at the time of starting a DC motor. In absence of any back EMF, it is only the armature resistance which will limit this current. Field current is no concern, because it is RL circuit, that initial transient, but it will steadily go to 2 ampere. What is the rated field current? It will have RF, we have estimated some 100 ohm. So, 200 by 101 ampere. There is no problem in the field circuit, it will settle down, but in the armature circuit it is. And always remember that field never participates in energy conversion. You apply voltage, it will develop. Therefore, the application of the voltage, the current will be armature current. If you plot, it will be something like this, IA. Apply the full voltage here, it goes to 400 ampere. After that, with time, it will decay down to finally to some steady value. Okay. So, what I have discussed in today's class is that given a DC machine, if you know the rating of a DC machine, which is a separately excited DC machine, and I will only assume that machine has been well designed. Therefore, I want to guess what will be the order of armature resistance, what should be the order of field circuit resistance. How did I do it? Assumed efficiency, some realistic figure, okay, very well designed machine 80% or things like that. Kilowatt rating was known, I calculated input power, total input power. Difference of these two must be the total losses at the rated condition. This is output, mind you, for a motor, mechanical output power. So, difference will give me the losses. Where are the primary losses takes place? Some losses will be in the armature circuit, some losses in the field circuit, and also some losses which will be rotational loss. And I do not have any idea about them, how they are really divided. Okay, let us assume, okay, 1/3, 1/3, 1/3. From that, I will get how much will be the power loss in the armature circuit. I can estimate always the rated current, okay, for this machine. Even rough estimation is 5 kilowatt divided by 200 volt. So, it is about 30 ampere. From that, I could guess the value of RA to be some 0.46 ohm or things like that, and that is absolutely, I am not claiming that will be the correct thing, exact value, that is what you will, but you will be expecting close by. It is not that I will not be struggling with the fact, is it not milliohm or is it not 5 ohm? No, it is of the order of 0.5 ohm, maybe 0.7 ohm also, okay, fine. Similarly, the field circuit resistance, Vf square by Rf is the field copper loss. Therefore, from that, if I know the voltage rating of the field circuit, I will be able to estimate Rf value. Rf value will be of the order of hundreds ohm. Anyway, today I stop here. We will continue our discussion of DC machine operations in my next class. Thank you.